Welcome back to the class on a power CV connected type. In the last class, we have discussed about the three-phase fully controlled converter with a DC motor, a firing angle less than the 90 degrees. In this class, we are going to discuss about the three-phase fully controlled converter, same load, by taking the firing angle greater than the 90 degrees. So this is the circuit diagram of the three-phase fully controlled converter. This is the load, and the current is passing from the top to the bottom. That is the positive direction of the load current. This is the field winding of a DC motor which is excited with a separate DC motor. So in the last class already we have seen how to draw the input voltage of a 6-line voltages. First you have to take the x-axis. On the x-axis you have to take the angle. This is the line which we have taken at a 0 degree. The same manner, this is the line we have taken as a 360 degrees. This is the positive. This line is representing the positive maximum value of a line voltage. This is the negative maximum value of line voltage. At every 60 degrees, we are going to draw the one vertical dotted line. Now we are going to draw the VAB. The starting point of the VAB is the 0. Next, we are drawing the VAC. The starting point for the VAC is the 60 degrees. Next, VBC. The starting point for the VB 140 degrees. Next, VBA. The starting point for the VBA is 180 degrees. Next, VCA. The starting point for the VCA is 240 degrees. The last one is the VCB. In the last class, we have seen how to draw these input voltage waveforms. Now, in this lecture, we have taken the firing angle more than the 90 degrees. So this is the knee voltage. Nothing but the firing angle which is applied to the T1 that we have to measure from this point 60. 60 plus 120, nothing but 180 degree, the T1 is on. T1 is on at 180 degrees. Once it is on, it has to conduct a 120 degrees. Next 120 degrees, T3 has to conduct. Because here 60 degrees, here 60 degrees. T3 has to conduct. Next 120 degrees, T5 has to conduct. This is the T5. We know that the delay angle between the T1 and T2 is 60 degrees. So the T2 is start conducting from this point. So T2 is conducting at this point. Once it is conducting, it has to conduct at 140 degrees. Next, T4 has to conduct. Nothing but in this duration, T4 is conducting. Next 120 degrees, T6 has to conduct. Next, we are going to mention the both positive group of SCRs and negative group of SCRs in every 60 degrees. T3, T4 is conducting here, first 60 degrees. Next 60 degrees, T5, T4. Next T5, T6. Next T1, T6. Next T1, T2. Next T3. Now we are going to develop the output voltage waveform. So first of all, you have to take the x-axis, and the x-axis we have taken the angle. Now 1 and 6 is conducting. First, we are going to identify the what is the waveform of the output voltage during the 60 degrees. I have taken the 60 degrees between the 180 to 240. Nothing but here I have taken the 180 to 240. In this interval, T1, T6 is conducting. Nothing but T1 and T6 is conducting. The output voltage becomes a VAB. How the VAB voltage varying? This is the 0. It is progressing in negative direction. I have taken the same waveform. So T1, T2 is conducting. The T1, T2 is conducting, and the output voltage becomes a VAC. So this is the waveform for the VAC. This is the waveform for the VAC. Next, T3, T2 is conducting. So the T3, T2 is conducting. The output voltage becomes a VBC. This is a VBC. Next, the same manner, I have to identify the remaining load voltage source. If you observe this output voltage waveform, this output voltage waveform always there in a negative only, nothing but the average of, if you find the average output voltage, that we are getting the negative voltage. So if the firing angle more than the 90 degrees, the average output voltage becomes a negative. But the current is always positive. The current is passing from top to the bottom only because this is a circuit which is allowing the current only from the top to the Got it. Next, we are going to draw the output current wave. Again, we have taken the x-axis, and the x-axis we have taken the omega t, nothing but angle. This is the output current wave. In this case, we have taken the load current is a constant load current. So this current is nothing but IBA. This is nothing but ICA. This is ICB. This is IAB. This is IAC. This is IBC. So already in the last class we have seen what is the meaning of IAB. Nothing but the current is starting from the A and return to the B phase to the load. Same manner, if you take the load current is ICB, the current is starting from the C phase, goes to the load and return to the B phase. The phase C current is nothing but a positive, whereas phase B current is nothing but a negative current, which is equal to the load current. Now we are going to see one phase current, phase A current. So from 180 to 300 degrees, nothing but from this point to this point, phase A is positive. So we have taken the phase A current is positive, that is equal to the load current. Here in this interval 300 to 360 degrees, the phase A is not supplying any current. So the phase A current becomes a 0. Again from 0 to 120 degrees, here the 0 to 120 degrees, the phase A current is negative because A is second subscript. Nothing but a load current is entering into the A phase. So here we have taken the negative current. Again here it is a 0. This is the waveform for the phase A current. The same manner we can draw the phase B, phase C also. So what is the expression we have derived in the last class? That is fully controlled converter with a DC motor for the constant load current. That is a 3 VML by pi cos alpha. The same expression also we can use. Characteristics of a shunt motor with a three-phase fully controlled converter. Already we have general expression for the motor speed. That is omega equal to V by K minus T RA by K. This voltage we are supplying it a three-phase fully controlled converter. Average voltage given by the three-phase fully controlled converter V equal to 3 VML by pi cos alpha. Now we are substituting this value here in place of T. We are getting the speed equal to 3 VML by pi K cos alpha minus T into RA by K. So the speed of a motor is a function of a firing angle now. As the firing angle changes, the speed of the motor also will be changes. Not only the firing angle, it is also depending upon the torque which is applied on the motor. Now we are going to draw the characteristics of a shunt motor with a three-phase fully controlled converter. On the x-axis we have taken the torque, on the y-axis we have taken the speed. Suppose if you take the firing angle alpha equal to 0, maximum voltage will be given by the three-phase fully controlled converter that we have taken as a rated voltage of a motor. So the rated speed will be given by the motor by taking the firing angle alpha equal to 0. When alpha equal to 0, this is speed torque characteristics of a motor. As the torque is increases, the speed of the motor will be decreases. This is the no load speed. This is the full load speed, this value. Suppose if you increase the alpha greater than the 0 and less than the 90 degrees. So I've taken the one more value, alpha equal 30 degrees. Now the voltage given by the motor at alpha equal 30 degrees will be lesser when compared to the firing angle 0 degrees. So from this value, the speed of the motor will be decreases as the load of the motor is increases. The same manner 60 degrees. At 90 degrees, this is the characteristics will be joining with a axis. This reason is nothing but a motoring operation. So where the power taken by the motor is positive, nothing but the machine will be operating in a motoring operation. Suppose if you make the firing angle more than the 90 degrees, let's take the alpha equal to 120 degrees, the average output voltage becomes a negative, but power becomes a negative because the current is positive, power is negative. It is given the regenerative braking. As the angle is increases, alpha equal to 150, alpha equal to 180 degrees. When alpha equal to 180 degrees, the output voltage becomes a negative. When alpha equal to 0 degree, how much voltage we are getting here? The same amount of voltage we are getting with a negative value when alpha equal to 180 degrees. The converter will be giving a negative voltage at alpha equal to 180 degrees. So the maximum amount of braking will be occurs when you are taking alpha equal to 180 degrees. Alpha equal to 180 degrees. So this is representing the regenerative braking of a separately excited DC motor or shunt motor with a three-phase fully controlled converter. In this case, we are assuming that continuous load current. Because in a three-phase fully controlled converter, there is a less chances to operate the drive in a discontinuous conduction. Already I have seen within the 360 degrees, the waveform is changing. Nothing but 60 degrees only the time gap is there. So within the 360 degrees, the current may not be come to the zero. Even though if you take the less amount of load to make the continuous load current, you have to add some external high amount of inductance in series with a load, so that the load current becomes a continuous. So before going to close this class, in this class we have discussed about the three-phase fully controlled converter by taking alpha equal to, here we have taken alpha equal to 120 degrees. We have seen the average output voltage becomes negative. The current is always positive. Power becomes negative. Nothing but it is given the braking operation. Next, we have seen the characteristics of a shunt motor with a three-phase fully controlled converter. Here, this converter is giving the two quadrant operation. One is the motoring operation, other one is the regenerative braking operation. This is the motoring operation, this is the regenerative braking operation. So thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I am always available to answer all your questions. Thank you.